Yeah, so today it's our pleasure to host Roberto Lalli. Roberto has been a research scholar at the Max Planck Institute for History of Science since 2013, and after receiving his master in physics in 2007, Roberto earned a PhD in international history at the University of Milan with a dissertation on the controversial reception of relativity theories in France and the USA. And from 2011 to 2013, Roberto was a postdoctoral fellow at the MIT under the supervision of David Kaiser, that we also hosted here. And he's an historian of modern physical sciences whose work focuses on the interconnection between social and epistemic factors in the production and circulation of novel products in theoretical physics. So please, Roberto, go ahead.
So thank you very much for the invitation. I now share the screen. I'm sorry that the lights are not very nice, but this is the time in Berlin. This is my situation at home. I hope you see the presentation now. Do you see full screen?
Yeah.
Yes, we can.
Okay, so thank you very much again. I should be clear from the introduction, I am an historian of modern physics, so more than a philosophical talk, I will be giving an historical talk on a work I've been pursuing for a few years on the process which has been known as the Renaissance of general relativity, with a lot of other people you can read in the slide. So what is the problem? Today, Einstein's theory of gravitation is universally considered one of the two pillars of modern physics, together with quantum mechanics. So while this is not very precise as an image, and we scientists should know that, this is an image which is ubiquitous. It is in popular books, it is in textbooks, it's also in some scientific periodicals. This image is often repeated. So the question is when, how, and why did general relativity come to occupy such a basic foundational position in our understanding of nature? The popular image, which is also widespread in scientific and philosophical circles, is that general relativity has been a building blocks of theoretical physics since November 1919. Namely, soon after, eminent British astronomers, including Arthur Eddington, you can see in the slide together with Einstein a few years later, and Frank Dyson confirmed one of the very few, three to be precise, empirical prediction of the theory at the time, namely, as you well know, the bending of light near the sun. While it is certainly true that this announcement launched the theory of general relativity as the first science mass phenomenon, including Einstein as the first superstardom of the icon of a genius in theoretical physics, the epistemic status of the theory was quite unsettled for a few years after this confirmation. The image that general relativity has become a major building blocks of our understanding of nature soon after this confirmation has been dismantled, disproved by historical scrutiny. A few years after the famous confirmation by British astronomers, actually the theory started to undergo a period of stagnation, which lasted quite a few decades, at least until the mid-1950s. Historian of physics John Eisenstadt called this period l'étiage in French, or the low water mark period of general relativity, and described it in a very specific term as a period in which Newtonian theory still was mainstream for many applications which were of interest or concerns to theoretical physicists. GR was admired for its elegant structure, for its logical and mathematical machinery, but was considered very difficult to handle, in particular by physicists. and then it became a marginal theory, purely understood, slow to develop, and productive both empirically and conceptually, to formal, to mathematical, to speculative, and these were few of the impressions that the theory generated to practitioners at the time. Now I give a short introduction to what are the main description of the theory by John Eisenstadt in this article and in other articles on the subject. So what were the features of research on generativity at the time? Well, first of all, there was a social component. Very few scientists work on the theory. The scientists were not only physicists, were mostly mathematicians, in some cases astronomers, and also even smaller cases, theoretical physicists. And they also worked in isolation among each other. Astronomers, mathematicians, and physicists had different reasons and also different knowledge baggage to work on the theory, and rarely communicated between each other. So there was a strong disciplinary divide between practitioners, but also some strong national divides, in particular since the 1930s, due to the changing political and economic condition in many countries which did actual science at the time. For this reason, there was the knowledge, the circulation knowledge was quite slow. Many of the results obtained in this period during the low water mark were rediscovered independently in the later years. And this gave reason to physicist and historian of physics, John Stacher, to invent a meta theorem, and I quote, "Anything worth discovering the field of generativity has been discovered independently at least twice, if not 3 tries." So this is, of course, true for many fields of knowledge in science, but it's particularly strikingly true for the theory of generativity, in particular the difference between discoveries or results obtained during the low water mark and the results obtained during the following period, which instead circulated quite rapidly among practitioners. This might be considered the social components of the low water mark period, but there were, of course, conceptual consequences. And Eisenstein argued that the theory was interpreted mostly in Newtonian terms, at least in 2 respects. First of all, it was considered for practical term only providing some minor correction to Newtonian celestial mechanics. Secondly, the more extreme prediction of the theory, the novel prediction of the theory, such as, for example, those we will later call the black holes, or at the beginning of the spatial singularity, the spatial metric, and gravitational waves, another example, were not trusted as possible actual physical phenomenon by practitioner. There was simply no belief that this extreme prediction of the theory were realizable in nature. There was much confusion about what was the physical status of this prediction for many years. So when did things change? And there is quite a lot of consensus that something started changing around the mid-1950s, and this was also perceived by practitioners themselves, in particular by a theoretical and experimental physicist Clifford Will, who famously called this period or revival of interest in the theory after the mid-1950s the Renaissance of generativity. This transformation looked so magnificent that it looked like a true Renaissance. And we can read Will's statement at the beginning of this essay called The Renaissance of Generativity. Despite its enormous influence on scientific thought in its early years, generativity had become a sterile, formalistic subject by the late 1950s, cut off from the mainstream of physics. Yet by 1970, it had become one of the most active and exciting branches of physics. There is about this interpretation of a transformation between a low water mark and the following period revival of Renaissance, there is quite a lot of consensus, which led to this kind of chronology. We are interested in the last 2 parts. namely the low watermark period in the Renaissance and the reasons, the characteristics of this change. While there is quite a lot of consensus among physicists and historians of physics that this change occurred, there is no consensus on which were the main causes or characteristics of this dramatic transformation in the status of the theory, in particular with respect to the mainstream of physics. There are many different approaches to understand this transformation. I mention here what are, according to me, the two most widespread explanations. The first one is that the Renaissance of generativity was simply a consequence of astrophysical discoveries, mostly serendipitous astrophysical discoveries made in the 1960s. The quasars, the discovery of cosmic background radiation, the discovery of pulsars, all this required, at least suggested that the need of a reliable theory of gravitation in order to be studied and understood. This in turn would, would imply, since these discoveries were all related to the advanced technological advances, in turn connected to the relevance of these technological advances for military matters since World War II, this would imply that the Renaissance of generativity was a consequence of technological advances, mostly military-related technological advances, which made for the first time the theory of generativity connected to the physical world in more interesting matters with respect to the famous classical tests of general relativity. There is a second, second widespread explanation which understands the Renaissance of generativity as a byproduct, a consequence of the general transformation of the physics landscape, the socio-economic physics landscape following World War II, following the relevance which physics obtained during World War II for military matter and then for national security. So, as you can see in the slide, and has been studied by David Kaiser, there was a tremendous increase of the numbers of PhDs per year, especially in the United States. This is an image of the United States environment, but not only in the United States. Of course, there was then an increase of talents and young scholars in theoretical physics, and also a flow of money within theoretical physics. So the claim is that this general change on the social landscape of physics also benefit the theory of general relativity, even though it was marginal before this momentous change. There are, of course, different possibilities to interpret this change, and David Kaiser, for example, has discussed, I think, in the BHI colloquium, one interesting nuanced aspect of this social change when private patrons, or also military related patrons, were interested in supporting the theory of generativity for their possible implication for the development of anti-gravitational devices. So these are the two widespread explanations. Both explanations are very sound, but they are in contradiction between each other for what concerns the chronology, because one would lead to think that the Renaissance of generativity occurred in the 1960s, while the second one would lead to think that there was a change occurring already soon after, or in the years after World War II. And how these two are connected is far from clear. So we have started a program which tried to provide a synthetic account of the Renaissance of generativity, trying to build on the many different explanations which have been provided, plus our own research on specific cases and on some synthetic view, which is what I will present here. Asking, for example, if the Renaissance was really purely a consequence of radical transformation of the social landscape of the technological advances, or if this transformation entailed some rather deep conceptual transformation on the theory itself, and how this connection between social and epistemic factors might have unfolded in the Renaissance process. In order to pursue this project, we rely quite heavily on the concept and techniques of network analysis. By doing so, we are within a recent trend in historical research, which try to use concept and tools of network theory in more formal and quantitative ways with respect to what was done in the past, when the network was mostly used by historians as a quite vague metaphor of complex historical social processes. So there is a new field which has emerged in the last years, which is called historical network research, which has since a few years also its own journal of historical network research, which tries to to bridge the traditional historical hermeneutics, the traditional hermeneutics of historical research with the formal and quantitative methods of network theory. So while we do connect with this trend, we recognize that most works within the historical network research field are mostly interested in social processes, in social networks. While I and other scholars involved in this project are interested in uncovering and studying networks of different types, which are all connected to the scientific activities. For this reason, we have developed a conceptual and methodological framework, which is called Socio-Epistemic Networks. This is based on the assumptions that the system of knowledge can be understood as complex system of encoded experience represented by material forms produced by actors in specific social settings. In other words, we tried to create a taxonomy of the layers of the network of knowledge based on three levels: the social network, or the actors, the social actors, both individuals and institutions; the semiotic networks, or the material representation of knowledge and the relations between them; and the semantic layer of the more abstract term of knowledge production, the concept research agendas and the semantic relations between them. All this might seem rather abstract, I understand this, but I'm trying now to show how we use it in practice in historical research. We try to find some proxies of the different layers, some entities which might be of relevance for the development of science in all the different layers. And we try to find proxies both at the level of entities, namely the nodes of the network, and of relations, namely the edges of the network. And here are some examples of the possible proxies we have used for different projects, or also for the project on the Renaissance or general relativity. And the social layers, is the social layer of the network knowledge is, of course, as main entities, the social actors, which might be person, individuals, institutions, commissions, formal groups, and the possible relations between them, which are, of course, include symmetric relations such as the collaboration or co-authorship in some particular works, but there may be also directed relations such as influence, PhD supervisor, PhD student relations, or there may be relation between different kinds of nodes. For example, the relation between individuals and institutions, such as the affiliation network. The semiotic network is, of course, less straightforward. We have to find proxies of the material representation of knowledge, the material products of some or any activity related to the knowledge production and circulation and so on. So some nodes which might be, as an example, publications, they are material production of knowledge, artifacts. Institution in some case can be also part of the nodes of the semiotic network, a possible connection between them. The most famous of which is, of course, the citation between papers. At the upper side of this three-layer taxonomy, there is the semantic network, which is the most abstract of the most abstract. And of course, in this case, we have to to find proxies in the semiotic, in the material representation of knowledge. For example, in words written in papers at the semiotic level. Such words might be the representation of specific concepts and may be related to each other, again, with proxies on the semiotic layer. For example, by their being occurring, or by being occurring in some bodies, in some parts of a corpus. At the most basic level, this kind of sorry, I come back to this. At the most basic level, this kind of taxonomy allows to create many more connections between nodes at the particular levels, because one might include a connection between the layers. For example, if two persons work on the same research agenda, we can create a new connection between these two actors, which will not be there if we look only on the social connection, for example. But this is only the basic gain. The idea is to use the most advanced formal and mathematical techniques of what is called the multi-layer networks theory in order to make some hypothesis on the causal relationship between the dynamics, the transformation between the different layers, and then test this hypothesis through empirical analysis of these networks. We are far from this more ambitious goal. We are still working on a previous phase of the project in which we tried to study the three different layers and try to build some formal connection and interpret them historically. So I start now by reporting what is our results on the dynamics of collaboration network in the theory of general relativity, in particular in the passage between the low water mark and the Renaissance phases. In order to do so, we use some basic assumptions which have been used also by others, for example, in some set of valuable papers by Bettencourt, Kaisers, and others, according to which we can hypothesize to study the emergence or development of specific scientific fields on the basis of the changes of the parameters of the social layer, namely of the collaboration network in this case. One example is the hypothesis that when a giant component, and you can see the giant component here as the component at the center of this network, which is simply as an example to show what a giant component looks like. When the giant component formed historically in the dynamics of collaboration, then we can assume or hypothesize that a field is emerged, a scientific field is formed, a scientific field which is connected to these social actors which are connected all together in the giant component, assuming that these people in the giant component share questions, tools, and concepts. The problem with the with the studies of collaboration network is usually that this collaboration network are coextensive with co-authorship network. The definition of collaboration is based on the fact that two people have published a paper together. While there are strong reasons to do so, mostly because this allows the availability of reliable data. It's quite problematic for historical research, especially when you want to study older periods and a quite larger time frame with respect to analysis of more recent and shorter periods. And we just want to do that. We want to study a larger period between 1925 to 1970. These are, of course, conventional dates which are connected to what historians and physicists have been stating about the beginning of the low water mark period. By the way, there are a lot of sense for claiming that in 1925 it was the beginning of the low water mark period, because it was the period when Heisenberg and Schrödinger published a paper which launched the quantum mechanics bandwagon. And the 1970, the end year of our time frame, which is the one used by Will in his famous article. So we want to study the dynamics of the collaboration network along this long and older period. And in order to do so, we couldn't stick on the co-authorship networks, but I defined other kind of collaboration and painstakingly tried to find by hand all this connection through historical research. And so these links include PhD student, PhD supervisor, kind of influence, which can be retrieved like acknowledgements in the first paper on general relativity and so on, other kinds of collaboration, and of course includes co-authorship. Besides this particular kind of collaboration, we also defined another kind of links between people, which is the fact that the people worked at the same institution at the same time. This created another kind of social relationship between scientists. So it's a very complex, multi-layer social network in its own right. And this kind of analysis allows to study the changes in the social network over time. Of course, there are many things one can do with this kind of approach, namely to study the structure in one specific period, in one specific year, and try to uncover which were the most relevant scholar using some centrality measure which network theory offers. Or to zooming on specific kind of relationship which are of interest for specific topics. But now, for the time being, what I want to report here is mostly the change in the structure of the network. So if we look at this image, for example, this is the collaboration network in 1959. We don't see any giant component. We see at least two largest components, which are most of the same size, which is the one in red, which is mostly based on the American groups, and the other one in green, which where in British Cambridge relative groups have a strong importance. But there are also other groups which are not connected. They're still quite large with respect to the general relativity research landscape. So the question is, when did a giant component emerge? And we studied the change over time of different parameters of the collaboration network. And on the result, which I think is quite straightforward, we studied the change over time, for example, of the nodes of edges of the entire network and the nodes of the edges of the largest component, in order to uncover when a giant component emerged in these dynamics. When exactly did the giant component emerge? So what this image in the slide show? We can see that soon after World War II, there was, yes, an increase in the number of people working on general relativity and also on the number of edges between them, a number of collaboration, but this didn't imply immediately a formation of a largest giant component. Namely, there were groups which grew at the time, but still remained unconnected to each other, while a radical, important change emerged quite a few years after World War II, namely at the end of the 1950s, and more specifically, in particular, between 1959 and 1960. And this is particularly evident if one looks at the bottom image, which is the derivative of the edges of the largest component over time, which show two peaks, and the first peak is in 1960. So first of all, this implies that there was such a change in the relativity community which were previous to the discovery of quasars. So in other words, it confirms that the social changes related to the World War II, on the follow-up of World War II, did have an impact on the theory of general relativity, and at least on the social level, quite radical impact. And also it might be assumed that the field related to general relativity emerged before the discovery of quasar. But it was not soon after World War II. It took a long time. So historians should look at the social phenomenon, social processes which led to this formation of the component. So this one first conclusion. We also have a sound hypothesis of what were these major social processes, but we can discuss this in the question and answer time if you're interested. Now, what I want to show is the second part of our analysis, namely the semiotic and semantic networks. We need some proxies to do so, and one proxy we identified as particularly promising is the using the co-citation network as a proxy of the semiotic network. The co-citation network is made by papers which are cited together by papers written almost always later the paper which are cited together. The more papers are cited together, the more strong the connection between them. And so we applied this method of studying the co-citation network and trying to uncover possible areas, so a possible cluster of co-cited papers which might be understood as intellectual basis of research fronts defined by the citing papers on this kind of corpus you see in the slide, which is the general relativity publication space, which grew quite rapidly after the 1950s. One first conclusion is given by the change of the structure of this semiotic layer constructed through the co-citation, the co-cited papers. So in different colors are different clusters identified with community detection algorithms of the using some specific algorithm of the network theory. And you can see we applied this clustering algorithm to the co-citation network in different periods. And you see here 3 periods which are particularly relevant in connection to the idea of the Renaissance phenomenon, because this includes the last years of the low water mark period and the first 5 years of the so-called Renaissance. And in fact, there is a strong structural change, which is quite evident. I'm not going into the detail of the different meaning of what are the different clusters about, but there is a structural change. There is the emergence of 46, the period 4650 of a core of papers strongly connected to each other, but this completely disappeared in the following period in 1951, 1955, while there is an increase of papers on general relativity or related to general relativity, but this shows a dispersed network of co-cited papers, actually with very few connection between the different clusters of co-cited papers. This change again, and this is where the Renaissance of relativity came up, is the change again in the period 56-60, when there is a formation of a different core of co-cited papers with a lot of clusters which are strongly connected to each other. There are parameters which show that it's very difficult to disentangle the different clusters, apart from 3 peripheral cluster of papers which are in fact not very much connected to general relativity. And we can see a different representation of the period of a co-citation network of the period 56-60, which is the most interesting one for what concerns the Renaissance phenomenon. And here, what is shown is that there is the emergence of this period of a relevant cluster, for example, the green one, which are connected to the prediction of general relativity, which were completely absent in the previous period. In this case, we tried to connect the semiotic layer with an interpretation of what this, interpretation at the semantic level of the meaning of each cluster of the co-cited paper. So there is the emergence of a core of clusters connected together, which are much more connected to the prediction of general relativity, which were there before. where general relativity actually didn't have much to do with the clusters of co-cited papers, were mostly clusters aimed at encompassing, going beyond general relativity, for example, in the quantization of relativity, or finding alternative cosmological model, or trying to define a unified field theory in the classical terms of gravitation and electromagnetism. Now I show the last image. I already took more time than given to me. So this is the last image in which is shown in historical terms the change of the co-citation clusters using different programs. Here are investigated a period between 47 to 74. You can see the arrow of time. There are clusters which are older, which are the one with a colder color, then which are mostly on attempts to kill the theory of general relativity, going beyond the theory, as I said earlier, namely attempt to quantize general relativity to find a different theory then, or to extend the theory of gravitation to include electromagnetism or alternative cosmological models. This kind of research agenda characterized the later years, or even the previous year, as we know, of the low water mark period. So what changed from the perspective of the source and conceptual level, of the research agenda level, or the semio-semantic level, according to our own taxonomy, is the formation in the period late 1950s, early 1960s of a giant cluster of papers, co-cited papers, all connected together, where the main focus is on prediction of general relativity, classical general relativity, or general relativity proper. Namely, there is a return, a conservative movement which came back to the theory of general relativity in order to maybe pursue later more ambitious project of going beyond the theory of general relativity. And this conservative move was strongly connected to the theorization of the gravitational radiation. And this is the element which might be characterized in the phases I shown before from the social level. Namely, what this shows that there was a reconfiguration of research agenda led by a social dynamics, a theoretical reconfiguration led by social dynamics. But there was a further change, which suggests to change the chronology I showed at the beginning, namely to include the third period, which was not there before, namely an astrophysical turn, a complete change of agendas which occurred in the 1960s. Later, and in consequence of discoveries in the astrophysical domain. Namely, there were the diversification of agenda, each of them connected to specific astrophysical discoveries or spurious discoveries in some cases, as I will show. Namely, there is a diversification in three major areas of research, one connected to relativistic astrophysics and the discovery of quasar, supermassive star. The other one connected to the discovery of cosmic background radiation and the cosmological model within the Big Bang model, like in gravitational instability. And the third one, which is maybe more interesting to you, was the formation of the field on rotating black holes, which was strongly connected not only to the theoretical works by Penrose and others, but also on the spurious discovery of Weber, because gravitational holes were, black holes were considered as possible source of gravitational waves. So there was a connection between one specific spurious discoveries in this case and the theoretical development which characterized this period, which I call the astrophysical turn of general relativity. So thank you very much for the attention. Here are a few publications you can look at for more in-depth explanation of what I tried to convey in this 35 minutes. Thanks a lot for the attention, and sorry for taking more time than 30 minutes.
Thank you, Roberto. That was a very nice, interesting historical perspective. So we're open for questions.
I'd like to ask a question, if I may.
Yeah.
Namely, you did not mention that in the end of 1957 was the start of the space age. And that had, I think, a major effect on a lot of what you're talking about, because it increased the money that went into training scientists and into science that was even more revolutionary than in the Second World War. Because the United States was so, how shall I put it, embarrassed by Sputnik 1 that it turned around enormously and put in a tremendous amount of money and effort into spurring scientific development, in particular in physics and astrophysics. How do you incorporate that into your general framework?
Okay, thank you very much for the remark. I completely agree that the Sputnik shock was a major and important event in sparking the many fields of research also connected to general relativity. But I still don't think that it's the major event in the Renaissance phase. And I think that the Renaissance phase started earlier on a different basis, and of course the space age increased this. But there was a change which was already going on, which later, thanks also to changes in the economic and social landscape, were led to a further increase of the theory. The work on the theory. If I can show here, for example, can I show a slide, for example? I'm still sharing, maybe.
I mean, I see the PowerPoint, yes.
Okay, so maybe I can show. So what I want to show is that there was a change which was already going on before the space age. Already the scientists working on generativity were start to build their own community. They start to build their own social community on a different basis, and this was not connected directly to the space age because it started earlier with conferences which occurred in 55, in 57, which were not directly related to this. So what I want to claim here is the Renaissance, as a Renaissance phenomenon, started earlier, and the space age had an impact, but it had an impact on what was already being created on different bases, and by such a group of people which explicitly tried to build a community on other sorry, I have a lot. Starting from other foundation. But thanks a lot for the remarks. Space age is of course an important part of the story. Maybe I stop sharing the screen.
I have a point. This is Gary Melnick.
Sure.
Yeah.
Go ahead. Well, I agree with Erwin. I was at Cornell University in the 1970s, and the architecture at the university tells the story. There was a huge boom in the expansion of buildings dedicated to physics, astronomy, and engineering post-Sputnik. The seeds may have been planted before Sputnik, but the funding to enable the growth of groups certainly was accelerated by Sputnik. And regarding your point early on about the competing effects of the emergence from sort of the low ebb mark of general relativity being due to the yet to grow community of astrophysicists working in general relativity versus technology. I remember Ed Salpeter, who was one of the two people along with Zeldovich who sought to explain quasars, saying that he searched quite hard to find people who were adept at doing general relativity calculations for his paper, but came up dry. There just weren't people available. So he undertook to teach himself how to do it, and out of which came his seminal paper. But I think that that speaks to the fact that that might not have happened had someone of lesser intellectual capabilities than Ed Salpeter undertaken that task. So I think that today, with the growth of the number of people adept at doing general relativity calculations, there is a natural explanation for why there are more papers on it, because there are more people who can meld ideas with detailed calculations than certainly was the case in the early 60s.
Okay, thanks. That was a comment.
We have a
comment.
We have a question from Peter.
I have a methodological question and a specific question. The methodological question is, if you had started with co-citation analysis, as developed by Henry Small and others starting in the early 70s, and simply divided up the subcommunities by co-citation, as was indicated in the one of your later diagrams, what would you miss not having done the more semiotic sociological network analysis that you began with? So that's a methods question. And the topical question is, mathematics doesn't seem to figure that much in the account. At least my, I think a usual understanding among historians of general relativity is that post-World War II, it was mostly the mathematicians that were interested in the development of general relativity. And and then in the Renaissance period, you had a very strong boost in its connections to physics, astrophysics, and so on, and applications like missile guidance and GPS and so on. So my question is, so those are the two parts of my questions. Is there a delta between what you would get from a pure co-citation analysis and what you would get introducing the sociological and semiotic degrees of analysis? And secondly, how do you see mathematics as figuring, or the mathematics of general relativity as figuring into this mix?
Oh, thanks a lot, Peter, for your question. So maybe I can share again. So for the co-citation analysis, I'm not sure if it makes sense to share. It might be helpful because these are diagrams, so the visualization is useful to convey something. So I try to share very quickly. So the co-citation analysis doesn't allow actually it allows to give some periodization, but as far as I know, and I tried to the different methods, these are those which allow to give more interpretable and visualizable, so conveyable interpretation to the audience, but doesn't allow to stick on specific and rapid change in specific years. So we see the map on periods, on periodization, which is quite broad and not very precise. So we can give a map more or less periodization, which we can understand also because we study the paper, and so we can understand where is the origin more or less. But this is a more or less a quite vague definition if we look at specific years. While here, what we wanted to do was very specific, namely the yearly change in the theory using very different hypotheses on the relevance of specific connection, on how long a link between people should last in our analysis. And we made really many different attempts and came up with the same result, which gives some specific changes in connection. So the change in connection which appear here will not be available with the co-citation network. So it gives a more fine-grained historical description, of course, only the social dynamics. So we don't have any clue, and at least we studied the papers they write together, what they were working together at the time. But we know which were the connection which created this group, and we know when this happened, and which were the processes which allowed this to happen in a specific period. So okay, I think that this is relevant in that that is not connected to a specific hypothesis on what were the knowledge production at the time, but mostly on what were the social conditions for the knowledge production. And the second question is the mathematics. The mathematics is not excluded by the picture itself. The network includes the mathematicians, but they disappeared probably in the citation network because of they were included when they were quoted within a larger physical area, I think. So they disappear, but they are there. But socially are there. But again, socially, the problem that socially they were in isolated groups until the Renaissance process, which created more cohesive groups, which were mostly based on physicists creating this group. And I can show you why more precisely. We have 1955, more or less, these groups, these centers, there's research centers working on generativity, which include mathematicians. Licknerowitz was a mathematician, Singer was a mathematician, although of course was very much expert on physics. But there were groups which were, Papapetru was in Pure Institute of Pure Mathematics, but included, of course, already physics. And I define research centers when there is a senior member with a permanent position, which is able to create students or also associate researcher. They were already existing or were emerging as a research center at the time, but with few, if any, connection between them. And what it changed in the later period between 55 and 62, they tried to change postdoc. And most of these postdoc were, some of them were mathematicians like Ivor Robinson, but were mostly then based on the physics research agendas. So they were also mathematicians, but mostly they moved from one place to another, and in moving, they shared research agendas, which became more and more connected to physics. And one major example of this return to physics is, of course, John Wheeler, as you know, which claimed strongly supported the connection with physics and trying to bring physics generativity into the physics landscape, increasing also the connection with other physics discipline. And I conclude that this was also a matter of harsh discussion between the person in the International Committee on General Relativity of Gravitation, when there was this committee formed in '59. Again, I don't see any connection with the space, this particular social phenomenon with the space age. These were people which were already meeting on the other basis. And then there was a strong controversy about which were the larger international union these commissions should be affiliated, whether the Union of Pure and Applied Physics or Mathematics or philosophy, philosophy instead of science. So there were a harsh controversy, and Wheeler and others, DeWitt and others, Bondi also, which was an applied mathematician actually at the time, strongly argued for the physics relation of the theory. So there was an explicit attempt by some people, which became more and more important in this phase, to connect generativity to physics, but mathematics is still there. I hope I replied to your question.
Thank you very much.
We have a final question from Shep.
Yeah, thanks. It's a very interesting talk. Just one point about mathematicians. So 1963 was not only the year that Martin Schmidt came with quasars, but also that was the Kerr solution year.
Yeah,
so that was a very interesting year for both mathematics and for observational confirmations of these quasars. The question I had is, as I was listening to your talk, I thought, what's next? Looking backwards, we can see where things came from, and this is a very interesting way to look at it. If you look forward, can you say anything, or dare you say anything about where things are going in the future? I mean, will there be a solution to the information paradox? Where are things going to take us based on this kind of analysis, but projected into the future? Or is that even a useful thing to think about?
Well, I have to be honest. I'm very modest in this respect. In the sense, I haven't had the ambition to see how this might be projected in the future. What we can do, we will tend to do, is to build more ambitious mathematical knowledge of network relation and see if they how they are connected to the empirical evidence in historical data, and if this is done, we'll explain it. If this is successful, we then maybe try to build some kind of hypothesis of how social connections, social changes are connected to changes in the concept. But apart from that, I don't think we can ever say something about resolution on this conceptual level. What I wanted to say is that this was a pilot project which was proposed by me and then done with others, expert in digital humanities, in network theory, and so on. So we had to build a shared knowledge, but we are now being supported by a three-year project to do much more advanced work. So this were we are still in the pilot phase, but there will be time to probably make more sound mathematical analysis of based on the network. But as far as your request is concerned, I don't think we will ever get that far. But I might be wrong. This is a nice question.
All right, thank you.
All right. If there are no more questions, let's thank our speaker again. Thank you, Roberto. And
thank you for the invitation.
Yeah, and happy Thanksgiving, everyone. Bye.
Happy Thanksgiving.
Fabio.
Bye-bye. Thank you, Max.